Hello and welcome to FEM Expert. Today we will present you a basic tutorial in which we will analyze a beam T-junction in Ansys. To begin with, as usual, we're going to use the Ansys instance. In this situation, we're going to analyze a T-junction made with beam type element. There's going to be defined by key points lines. And we're going to introduce a couple of new functions like the working planes, and that are very useful, especially when you're working with more complex models. So the first thing we're going to do is to define the first beam. We're going to define key points. In order to do that, we're going to go to preprocessor, modeling, create key points in active CS, which means the active coordinate system, which is the one that you can see in the monitor. And for the reference of the one that you're using to work, you can have it here. The 0 means this one in active CS, and here we're gonna do the key point number 1 is gonna be at 0, 0, 0. We apply, and key point number 2 is gonna be at 0.4, 0.8 meters. No, it's gonna be a 1 meter, sorry, on the X direction. We can see both of the key points. We're going to use the isometric view to see them properly, and on this, with these two key points, we're going to define a line. We're going to do that. You go to lines, straight lines, and double and click on each one of the key points, and you have the line. If you zoom in, zoom out, or move the model, you're going to lose the lines. You can always plot the lines or the key points, or you can go here and use the gplot, which means global plot, that shows you the lines and the key points. This is usually a better way to work because the global plot allows you, especially if the models are easy, allows you to see what's happening everywhere. Okay, so now what we're going to do is the next step is going to be, we're going to use the work plane. We're going to create a separation. We're going to create an intermediate key point in between these two key points, separating these lines into two segments, in order to create a transversal beam. For doing that, we can use diverse methods, but we're going to introduce the working plane. If you go to work plane and display working plane, you'll see there's another, in the original coordinate system, there's another working plane. This work plane is very helpful, especially for certain operations when you want to cut or modify things or create different entities, and for creating circles and other stuff, or for changing your coordinate system to a local coordinate system that you can just move wherever you want, and so on. So what we're going to do now is we want to move this coordinate system to the right place. What we're going to do is go to the working plane, offset work plane by increments. And here what we have to do is we're going to put 0.8 millimeters, and it's going to be on the X axis. You can put commas and do the offset on the other axis, but because we don't need it, we're just going to do 0.8 and hit OK. And now you can see that this coordinate system has moved. It's clearly different from this one. It's orientated the same way, but we're not going to use it this way right now. Because in order to perform the cuts are only performed along the X-Y axis. So if we would like to perform a cut through this beam right now, we will get an error. Actually, we can try that. We're gonna go to perform those cuts. You gotta go to operate, booleans, and you gotta go to divide. And what we're going to divide is a line. You have a lot of options here, but here we're going to divide a line by a work plane. You hit that, you select the line you want to divide, you hit OK, and you'll see that there's an error, and you're like, because you're trying to divide this line with a tolerance, it doesn't make sense. Okay, so what we have to do is go to work plane again, get this menu here, and we're going to rotate this. We're going to rotate this the work plane. Okay, so in order to rotate this plane, we have to have the XY has to go perpendicular to the beam. So in order to do that, we're going to go here. Here we have the angle value. By default is on 30. We want to put it on 90. And we're going to rotate the plane along the Y axis. around the y-axis. We do that, and as you'll see, we have the plane rotated. You can do it again, or you can do it this way, it doesn't matter. As long as the XY plane intersects, you're gonna cut everything that intersects the XY plane. We hit OK. Now we're gonna do the same thing, divide line by work plane. We select the work plane, we hit OK, and you'll see that we have two lines. We're gonna go to work plane and we're gonna not see the work plane. And as you can see, we have two lines with two different colors and 3 key points. The next step is now we're gonna create key points on both of the sides of the Z axis. For doing that, we're gonna use the copy option. So we're gonna go to copy. We're gonna copy this key point on the Z direction. The first one is gonna be at 0.5, and the next one is gonna be at minus 0.5. Again, we go to the G-plot, and we have our model. What we have to do now is go to lines, create lines, straight lines, and we create this first line and then this second line, and you will see that we have our model properly made. This little T-junction can be, the dimensions could be different, it doesn't matter, it's just an example, so you just have to get the idea. Okay, so now we have the model, and we have to define the element types and everything. So we're gonna go to the element types, add the delete, add, I'm gonna select beam, 2 nodes 188, okay, close. No real constants for this element type, so we're gonna go material properties, material models, and we're gonna get here, we're gonna define a structural, linear, elastic, isotropic material, 2.111 Young's modulus, and 0.3 the Poisson's coefficient for steel. Also, we're going to define a density, 708,000 kilograms per cubic meter. And now that we have the material defined, we have to define the sections. In this situation, the beams require sections, so we're going to define for the beams a common section 1, we're going to call it 40 by 40 by 3, and it's going to be a hollow rectangular profile, 40 by 40 by 3 millimeters. So we're going to define this in accordance to this diagram as 40 divided by 1,000, 40 divided by 1,000, because we're working in meters in our system and we're putting millimeters in the profile of the beam. 3 divided by 1,000 the thickness, and all of the thicknesses, as you can see, the beam asks you for every thickness of every wall of the profile. We're gonna hit OK. You can always preview this and see if you define your profile the right way. We're gonna go back and hit G-plot, sorry for that. We're gonna raise the hidden menu and we're gonna hit OK. So now this section has been applied. At this point, we have everything we need for the model, but we haven't told Ansys which beams have what materials or what are the properties of each part of the model. So in order to do that, we're going to go to mesh attributes. We're going to pick the lines. We're going to pick them all right now. We're going to select the materials number 1, no real constants, the type of element is 188, and the section is 40 by 40 by 3 millimeters. We don't want to pick the key orientation, so we just hit OK. Okay, so now Ansys knows that this beam or this model has these properties. The next step is to go and mesh this model. In order to do that, we can use the mesh tool. We're going to use the mesh tool, so we're going to set the global size for the lines. Pick all the lines as 10 millimeters, so 10 divided by 1,000. We hit OK. We're going to see that they change a little bit and we kind of can see the size of them. Actually, if you zoom in, you'll see the divisions, and this represents the size of each one of the elements. We're going to go raise the hidden menu, and we're going to go to mesh again. And now we're going to pick all. And now the model has been meshed because you can see we have elements. If you go to G-plot, you'll see elements, lines, key points, and nodes. At this point, because we have so many nodes, the global plot is not an option, so the best thing to do is to go and plot elements. In fact, if you go to the plot controls, style, size and shape, and you activate the each shape option, I'm gonna close this too. Okay, what you're gonna see is the actual junction with the correct profile sizes. Okay, I'm gonna deactivate this option right now. So style, size and shape, each shape off. Okay, and now we're gonna proceed to simulate the model. What we're going to do is go to solution, analysis type by default should be on static. You can do this or not, it doesn't matter. I'm just showing it to you. We're gonna define, not solution control, sorry, cancel, define the loads. We're gonna apply a structural displacement restriction on this key point, here. All degrees of freedom, they're gonna be 0. Okay, we restricted the junction at that end, and now we are going to apply a force on this key point here. On key points, that key point on the y direction is going to be minus 100 Newton. Okay, we see the force going downwards, we have the restriction of the junction, and now what we have to do is solve this model. So solution solve, current ls, okay. Tell us that the solution is done. So what we have to do now is go to general post-processing, read results, last set, plot results, counterplot, nodal solution, degrees of freedom solution, displacements, vectors sum. Hit OK. And as you could see, we have the displacement, the summation of displacement. The biggest displacement takes place at the end where the force was introduced, and the smallest displacement at the junction, at the restriction. Also, if we go to nodal solution and we try to see the von Mises the stress, you'll have a little surprise here. You see that Ansys doesn't plot anything. This is because in order to see the stress, you have to go and activate the each shape option. So go to plot controls, style, size and shape, each shape, okay. And now you can see the von Mises the stress. As it would be normal, the biggest stress takes place where the embedment is, and the smallest stress is where the force is applied. Okay, so now the last thing I'm going to show you is going to do a vector plot. I'm going to deactivate the size and shape, each shape option again, and I'm going to go to predefine a translation plot. This translation plot should clearly show us how this beam is being deformed. It is quite useful when you're analyzing complex shapes, and as you could see, the deflection on the transversal beam is exactly the same as at the origin where the two beams intersect, which makes sense. So now with this, we're gonna end this tutorial. I'll quit and no save. So now you know how to use the working planes and how to perform a simple beam simulation in Ansys. We would like to thank you for your attention, and we hope you enjoyed this presentation. For more tutorials, please check our community and follow us on the social networks.